All right, let's talk about retrieval requirements for Filecoin SPs. Luckily, this will actually be quite short, so I think we can get back on time. What is the correct ending point? So I can. So at 15, at 2:15. Yeah. Great. So this is what we'll go through. Types of retrieval in terms of tiers and help orient us in terms of the storage market and the retrieval market, like what kind of retrieval must the storage market do. We'll talk about content, what should be retrievable. We'll talk about the different data structures. We're going to talk about the gap. Currently, we don't verify the retrievability of the content, and that is a gap that needs to be closed. We're going to talk about some cryptographic tools and the limitations. You already heard a little bit about that earlier. And then we'll talk about the kind of like the only real way to solve this, which is networks of retrieval verifiers. And I'll kind of like set the stage for a very concrete set of descriptions later. So I won't kind of like give you I won't pitch you a particular retrieval verifier network, but other people will. Cool. So let's start with kind of orienting ourselves in terms of the scales of speed in terms of latency. Like when we think about latency, what are we talking about? These are different orders of magnitude of retrievability against different kinds of storage media, whether it's a physical device and an actual like physical process that you're pulling data from, or you're thinking about it potentially as a network and you're pulling something from the internet. So at the very top, like in the extremely fast scales, we're talking about nanoseconds, and that means actual CPU speeds. This starts getting into like L1 caches and so on. Getting into the tens of nanoseconds, you start getting into like moving out into like L2s and so on. This is still only just in hardware. This is not L2s in blockchains. This is L2s in hardware. Skipping a few orders of magnitude, we start getting, once you start jumping from one physical device into another physical device, you start hitting the hundreds of milliseconds or nanoseconds. Hundreds of microseconds or milliseconds. Important to get your SI units right. When you're going to move from, say, one computer in one room to another computer in the same room, you can maybe get it. There's a famous description from Grace Hopper talking about a nanosecond being about this long, and the idea of that is that a nanosecond is the distance that that light requires to travel at that speed. So when you think about a room, for my computer to talk to another computer over there, there's like a bunch of nanoseconds in between here and there, and that's the fastest you could possibly get it based on speed of light. So when you think about a data center, and you think of like two computers in like right next to each other, like it's usually about like a nanosecond or two that it takes to go from one to the other, because you also have some other delays in terms of switching. Once you start going outside of that building to another building, you start getting the tens of nanoseconds. That gets a lot worse. Sorry, milliseconds. At that point, you're starting talking about milliseconds. I'm jumping between the orders of magnitude here a lot, and I'm confusing myself. Well, that nanosecond to millisecond delay comes a lot from all of the layers of software that your packets have to go through. And so once you're in kind of different pieces of hardware, or you're going to different buildings, you're in the kind of tens of milliseconds to eventually, once you go across the country, hundreds of milliseconds scale. And that's a totally different landscape to be in. Still, if you're going to try and retrieve something around the world, then you jump into the 200 to 300 millisecond range. And at that point, you're among the kind of like slowest things in computing. But that's kind of like what it looks like to pull something from around the world. Now, for most large-scale applications, you want to pull the data close to you and then retrieve it frequently in that area, right? So if you think about any kind of major application where you're going to have the same content be retrieved many times, so think of like what a video on a video website like YouTube or something like that, or a movie, then you want to take the content from wherever the origin is, and you want to push it close to the edges of where people are going to be to watch it, as close as you can to them. And so that usually means into data centers close to the locations where it's going to be retrieved a lot. So ideally, your computer, if you're going to load something, is only going to some other data center in your region to retrieve it. So now that requires tens of data centers. So that means the content needs to be in tens of places around the world, and that looks like a CDN. That's for the hot content. That's not for the normal data storage process when you might have somewhere between 3 to 10 copies or something like that. If you have 3 to 10 copies, you're really in the kind of 100 millisecond to 300 millisecond range, and that's kind of the overall target. Does that kind of make sense to everybody? I'm guessing so. So all of this kind of splits up into kind of the traditional storage cloud set of products and then the CDN set of products. Now, we're not kind of thinking about here the things closer to the user, which are kind of like the actual physical device and so on. That's a whole different problem. And so the Filecoin network thinks of modeling the storage side as the storage market, kind of like the cloud storage products as the storage market, and models the CDN market as the retrieval market. Another way of looking at this is kind of like this. So this is just looking at the storage products and the CDN products, and you can think of like the storage providers as like mapping to those specific regions, and over time kind of like getting closer and closer to the kind of like 100 millisecond to 50 millisecond retrieval latency. And this is kind of plotted against cost or capacity. And when you think about CDNs, like what you really want is a ton of small machines with really high bandwidth and very low latency, but usually not a lot of storage, right? So you think of CDN nodes as being the ones that have low terabytes, like hundreds of gigabytes to maybe a petabyte in scale, very, very close to the user, usually storing a cached copy of something, maybe running some edge functions or something like that, but they're not going to be storing a huge amount of data. The large amount of data is going to be in SPs. Now, because one of these is called the storage market and the other one is called the retrieval market, don't mistake and think that the retrieval market is the only one doing retrievals. The storage market has to retrieve the data, because otherwise, if you just put the data in, you can't get it out. So SPs have to serve the data as well. It's just not with extremely high bandwidth or a ton of requests and so on, right? So it's a kind of some baseline level of service level agreements of being able to at least serve the data with some reasonable latency, reasonable here being kind of in the 50 to 300 millisecond range, depending on kind of where the client is retrieving from. And with some reasonable amount of bandwidth. Reasonable here means being able to serve the data using some kind of like stock. The kind of numbers here tend to change, but you want to be able to use in the gigabits, in the tens of gigabit, single to 10 gigabit line type of bandwidth capacities. And you don't need to kind of offer serving the data tons of times to the same user. Like that's definitely, if somebody's going to be retrieving the same data tons of times, that qualifies as more the CDN product. Does that kind of make sense? Any questions here on like the mapping between these two? And notice that there is some significant overlap between them. But yeah, and any questions on the mapping here or responsibilities? Yep. Sorry, this is an old diagram from when we were talking about two different, there were NSCs and an old POREP. Actually, it was a newer POREP than SDR. It ended up never shipping. SDR is a POREP. And so that's where like the extra copy piece comes from. Ideally, we can make much better proofs of replication so that the POREP doesn't introduce this huge latency cost, right? So like the reason that's so bad right now in the kind of like minutes to hours is because of the POREP. If we had a much better POREP, that could come down significantly. I claim that good POREPs will get us down to in the order of like 40 milliseconds sealing and retrieving. And that's kind of where we need to get to. It's hard to get there, but I think that's what you need in order to be able to like properly meet the storage media requirements. But that's not the world today, right? Like the world today, you solve it by storing an extra copy. So you have a sealed copy and an extra copy in the clear. But good question. Any other question? Sweet. Cool. So the point here is storage providers must provide the data with some reasonable latency, some reasonable bandwidth. Now, what content should be retrievable? There's a bunch of different kinds of data structures. When you think about the user's data, the user has their own set of data structures and models for how they reason about the data. But either way, they're constructing some payload and giving it to Filecoin. That payload is usually addressed by a CID. And we take that and we put it into a Filecoin deal. Usually we use a thing called a piece to then construct a proving tree for the storage proving process. You then grab those pieces, pull them together into sectors, and then separately from that, we're indexing this entire operation by indexing the sectors. We know all the sectors that are in the network. We index the pieces. We know all the pieces that are in the network. We index the actual payloads using the indexing processes that we added in the last year or two to actually index all of the individual CIDs in the payloads. And we maintain those indices on the side. This is known as IPNI. The retrievability here, so the question as to what should we check when we talk about retrievability checking. At the end of the day, what the user cares about being able to retrieve is their data. So we should be able to check the retrievability of the user payload. That means if there are CIDs in the payload, A, we should index those, and B, we should check retrievability of the individual CIDs with random access. That's not the piece, it's not the proving tree, it's not the sector, it's the individual objects addressed by CID in the payload. That's what the user is saying they want retrievability over. They're saying, here's a data structure, I want retrievability over this data structure, please give me random access by the CID. Does that kind of make sense to everybody? Any questions on this kind of retrievability checking piece? Yep.
I just want to note they also want ranges of seeds too.
They also want ranges. Yeah. You should be able to provide retrieval of specific ranges. And yeah, so that's the point there being the retrieval checkers should potentially check for specific ranges and check the latency on retrieving a particular range. Yeah, that's a good point. Yep. Yep.
And the layers, the many layers cause a lot of
yeah, so the user data payload here, there's some mapping between the user data structures into the objects that are going to a car file. And sometimes that mapping is good. Like, for example, if you take a tar file, you can map it into a car file cleanly and have a different object per header in the tar file. Sometimes that mapping is really bad. You take a huge flat file and then just then dump it into, you chunk it using like a bad chunking thing and then give it access. That default process at least gives you the graph that you need in order to do random access into that object, right? So the graph that you end up with in the payload is a graph that lets you do random access retrieval into that large flat file. And that large flat file could be enormous. It could be like, petabytes in size, but it will be chunked into pieces and then put into a car file. At least, with some default, that's a kind of a default version that works reasonably well. It's not the best. Ideally, you would be mapping the user's own data structures into the IPLD data structures to provide precise random access to precisely the things they care about. So for example, it would be pretty cool to map, say, using the Internet Archive as an example, map the individual objects from the Internet Archive's own data structures of the work files and all the different versions of a particular site and so on, and create an IPLD representation of that to then provide perfect random access to all of those data structures and be able to check retrievability of all of that. Cool. Let's move on. I guess one piece here. There is a case to be made for the pieces themselves and the sectors, including the sealed sectors, being retrievable. And the example is if you have capacity being advertised in the network, you should be checking the retrievability of that capacity. Otherwise, it might not be real capacity. If a party is advertising capacity to be able to store data, but isn't willing to verify the retrievability of that capacity, is that real capacity, or is that just fake capacity? So there's a case to be made here that for CC sectors themselves, the network should be checking retrievability. And at that point, you would be checking the sealed payload. There's another example like that where you might be able to, if you do a mapping of objects that are in different locations within sealed sectors, and an SP does not want to unseal something to give it to you, you could be able to you could potentially extract the sector and then unseal it yourself. So there's another case to be made for being able to retrieve normal sealed sectors as well. But kind of the order of priority is like first the user data, then after that maybe capacity sectors, and then after that other sectors. Yeah. The difference is that the piece itself, like the problem with relying on the piece is that the piece is highly dependent on the particular POREP. So if you build a system that is dependent on the piece abstraction and how the proving tree works, and then you go and change the POREP, your system might be obsoleted by that. And so it's not a good abstraction to lean on. So we should probably have a separate discussion later on, whether in this track or a future track, about where to lean on the pieces and when not to. But just like in general, I strongly advise against leaning on the proving tree for anything other than storage, for the storage proving, because that entire tree and its shape is liable to change with a new POREP completely. And so any assumptions that you have about it might not survive. And so if you build an entire retrieval checker system and retrievability system that depends on a particular POREP, and then you change that POREP, your entire other system has to change too. So that's not an abstraction you should build on. What you should build on is the CIDs, the payload CIDs, and maybe the root CID of the thing. Those are the only guarantees. But it's a great question. Cool. Let's talk about verifying retrievability. So currently, retrieval is not verified. So this is kind of like a graph from the Retrievalbot checker from the Falcon Plus program, and this is not a good place to be. We need to get to a point where all of this is green. It's great that we now have this tool to be able to see the retrievability of this data. But this means like SPs are not honoring the agreement, right? So with Fil Plus, your SPs are supposed to allow retrievability of the data. That's part of the agreement of the Fil Plus deal. But this is not working. A, because it wasn't kind of really checked until very recently. B, because it's not being checked that well. We need to check it much better. And C, because the incentives are not correctly tied to this. So there's no actual significant incentive penalty for not honoring the deal. So if SPs don't promise to serve the content, but then don't serve it to you, and you have the protocol does not have any, currently does not have any facility for addressing that problem. The way that, for example, the protocol addresses storage faults, right? So if storage disappears, there's a storage fault, and there's a correct protocol process to address it. Currently, the protocol does not have a way of addressing this kind of retrievability fault. So we need to kind of close the gap to be able to make this data the retrievability checkable, and connect it to incentives. So a key piece here is the retrievability of the storage is already incentivized by the File Plus multiplier. It's supposed to be paying for the retrieval already. And so that's just not, we need to be able to close this loop, checking the retrievability and affecting the power based on the retrievability scores. And so in order to get there, we have to first build a pretty robust retrieval checker system that we actually think is really good, works, everybody can check and trust that it's actually correct. and then from there weave that score, the retrievability score, into the block reward incentives as they are today. Yeah, question?
Yeah, question. Between June and now, the ratio of every bar, it used to be 0% total size of deals from clients with a score of 0%. So the red bar, the ratio of the red bar to the size of the total is dropping. It looks like it's eyeballing a third. I feel like if you look at,
Yep.
June 8th to now.
So it's getting better.
So I was going to say, what's caused that improvement?
I would defer to the quality folks in the great quality folks in the Filecoin Plus program. Yeah.
When we started checking the retrievals using retrieval bots.
So this means Retrievability starting to check things and starting to force some better compliance.
So basically, if the retrieval bot is not score that you get as an SP is not high enough, then you don't get further data tapped out.
Yeah.
So why did the ratio change so much between necessarily orange and yellow, or yellow and light green and dark green? The real ratio change seemed to be from like red, a lot of red became orange.
Yep.
So when people like really started to like try to enable retrievals, but they're kind of somewhere in the middle. They're not really green. Green means like 100% or 75%. They're really, really good at it. But at least the reds are really like small now. That means at least people are trying. They don't know exactly what the best way is to, enable retrievals, but they're trying.
Yep.
My SPs didn't know about the booster services.
Yep. Yeah, there's a lot of factors here that are likely affecting this. Yeah, question over there?
Maybe a dumb question. I mean, like, to load dates, the results of some graph, what does it represent?
This represents there's a set of bots that are checking the retrievability of data stored on Filecoin Plus. They're just randomly sampling a set of content and checking that it's retrievable. And this system is like is much better than prior systems, and certainly much better than nothing, but it's not yet robust enough to be able to check the entire data set at the frequency that we need it.
No, I got
Yeah.
to what the graph itself represents. I mean, like, like below the date.
Blue graph.
The blue graph.
The
Yeah.
red line.
Huh?
It's just the red line again.
Okay. I mean, yeah, that's.
Yeah, I missed that, but I'll move on. Cool. So let's talk very briefly about cryptographic tools and networks. So Will mentioned that we don't have cryptographic tools to solve this problem, and that's because you can't use cryptography to check what is fundamentally a network-oriented problem, where you have different parties trying to get some data, and at the end of the day, when you retrieve something, you're talking about a process of bytes moving from one location to another location. So you immediately have to start answering the question of like, what locations do you mean retrieving from? And at what rate are the bytes coming through in, and so on. So unfortunately, the retrieval problem is one based on networks. However, there are some cryptographic tools that you can use to help you solve the problem. I'll give just a quick plug for proofs of retrievability here. So there's a whole kind of world of different types of proofs of storage. This is one kind of Venn-style diagram describing some of them. Other people have different diagrams, so this is kind of like my conception of it. Within the world of proof of storage, you have proofs of space. Within kind of intersecting with that, you have proofs of data possession. A subset of those happen to be proofs of retrievability, or a different subset happen to be proofs of replication. Proofs of replication there, and like why they're interesting, is that they are this intersection between proofs of data possession and proofs of space. All of these have like very concrete cryptographic definitions. Like the high-level idea is like proofs of storage is just the general class of proofs like this. Data possession is proving that you have access to some particular set of bytes, but you're not kind of leaking any information about them. Proofs of retrievability leak some of the information about the objects themselves in the response, so you can use the proofs themselves to extract the object if the object is small enough. Proofs of replication give you strong space guarantees that a certain amount of physical space is being used, and while giving you this data possession on top. Proofs of space is the general class of just spending some energy resource, which might not be like useful. It might be wasteful. And then proofs of spacetime is just a technique to use any kind of proof of storage in an iterated way to verify that that's happening across long periods of time. So it's kind of like a quick, very hand-wavy description of these types of proofs. So the ones that we want to use in the retrieval checking problem are really proofs of data possession or proofs of retrievability. Both of those have really good, very cheap cryptographic protocols that we can use. We should not really be using proofs of replication. Those are extremely expensive. Don't need any proof of space or anything like that. You really want to use PDPs or proofs of retrievability. And there are some compact ones, especially proofs of retrievability have a compact protocol using BLS signatures that I think could work really, really well. Anyway, the network today does verifying of storage every day, right? So every day, the network checks that all of the storage is being correctly stored. And we do this using some probabilistic sampling. For every sector, we randomly check a small number of sites, and we check that they have been correctly stored and are correctly encoded. And we use that statistical information to then make a claim about all of the sectors in the entire network. So we have a graph that shows what storage is being stored at any given point in time. We need a similar graph like that over time for retrievability. It would be great to be able to get to the point where we can check the retrievability of the entire Filecoin data set, like all of it, all of the data that's stored in Filecoin, from everywhere in the world. Asterisk there are some parties that want their data only retrievable in certain locations, and there are ways of addressing that. But we should be able to generate a graph that shows the retrievability of all of the data in the network statistically sampled, right? So you should be able to randomly check for specific kinds of checks and be able to gain enough certainty over the entire data set to then be able to make a confident cryptographic claim about the retrievability of the entire thing. So the way to do that is through networks. We want to get to a point where we have this kind of sampling at scale. We should be able to build, sorry, I think it's not quite, oh, there we go. We should be able to sample the entire network at scale, and so that means having a network of nodes that is going to be running this verification process to then randomly sample some component to check, and then running that check and reporting the result. And out of a large amount of these checks, we can then get some statistical statements about the entire data set in the network to then be able to see what's working, what's not working, and then be able to potentially even give measurements. So like not even like is this retrievable or not, but it's rather it's retrievable with this kind of latency or this kind of bandwidth. And that starts making the product dramatically more useful to end users. And I think a plug here is like you can use things like FPC and so on to build subnets to be able to do this checking, to then kind of recruit a large network of nodes to be able to do this kind of stuff. Similar to how Saturn is doing it, right? So Saturn is building a kind of an L2 network with a bunch of other retrieval providers that are doing this retrievability of the data for the CDN use case. You can follow a very similar kind of pattern to then do the verification of the entire data set. I think Patrick has some really good graphs that he and other people worked on that show kind of like measuring of the retrievability of a bunch of different content from very different locations. That was kind of measuring different gateways. Now imagine that, but across like all SPs, across all sectors. That's kind of where that is headed. All right, that's it. Thank you. Yeah.
For the network of retrievers and so on, how do you ensure that that the storage provider isn't just providing retrievability to the checkers and not providing it to like anybody else who might want it?
That is a great question that we will hear more about once we have a concrete example being provided. The general class of problems, you can use things like randomness to select which verifiers are going to verify what. And yeah, you have to think about the sampling there.
So every time we check an SP, we randomly generate an IP address, so the SP cannot just like allow list this peer ID because every time it's different.
But in that case, you're running those retrieval bots, and in the case that he was talking about, we're talking about a network of random verifiers that are not trusted. So a trustless network of verifiers.
Yeah.
Yep.
Thank you. To reach this level of latency that we are mentioning, does it mean that we, in the close future, we keep this unsealed copy? We are still working with unsealed data. And that's my first question. And the second one is like, how do we protect, are we ensuring that the SP is having this unsealed copy and not just proxying data from another one?
So it's a good question. So the first part of the question is, are SP supposed to keep that extra unsealed copy? Yeah, in the case of Filecoin Plus, can I get the slides back? In the case of Filecoin Plus data, they are supposed to be storing unsealed copies. That's part of the Filecoin Plus agreement, and that's kind of why part of where like that 10x greater reward goes to is pays for the cost of that extra copy and a bunch more operations. And so yeah, it's supposed to be checked. There was a goal to check that in the storage process. You can actually use the storage verification process to check that extra copy. Now to your second point, how do you verify that they're not just kind of accessing it from somebody else? Without strong latency bounds there, you can't really. So you can't really do that well. So you could have a case where like there's a certain set of parties that have the kind of sealed copy and then they're sharing kind of the unsealed copy. That's more okay because at the end of the day, you're really paying for the space on the sealed one and you're really paying for the accessibility on the other one. So it's not great, but it's not, we're not relying on that extra copy for redundancy. So that number is not kind of helping the redundancy. So that would be a hole in the protocol, but it's not a very big one, and it's not that. At the end of the day, if you can pass a retrievability check, that's the most important part, and that's going to have some latency guarantees, right? So they might be able to pull that copy from somebody else, but the other party has to be very close, because if you start checking this from like very close to them, then they're not going to have a lot of time to go and get the copy from somebody else to then serve it. So being able to kind of have networks of verifiers that are in the same, within like 10 milliseconds of them or something like that, that would be excellent.
Cool, thank you.
All right, thanks.